Okay, so welcome everyone also to our virtual seminar. It's the first time we are also live streaming this to YouTube. It's our great pleasure to have Ben Bose from the University of Geneva, who is gonna talk about game of gravities, disputing dark energy with galaxy surveys. Please go ahead.
Thanks, Julian. So I chose the title because I am a Game of Thrones fan, and it's been 1 year since that season, since last season aired. So for those of you who like Game of Thrones, there are tons of references in this talk. For those of you who don't worry, there's some science too. So without further ado, I'll start. So I'll be talking about some work I've been doing over the past year, which has recently come out on the archive. And it has to do, as the talk suggests, with testing gravity using galaxy surveys. And so I'll start with some basic motivation. So we have this really lovely picture of galaxies we see in the night sky. And from that, we want to learn about gravity, and we also want to learn about the evolution of our universe and the model that best describes it. And the current model that we use to describe this is the lambda CDM model. And as we know as cosmologists, that model does have some issues. So namely, well, the biggest issue is that if we were to accept general relativity as the theory of gravity, and within the standard paradigm, we need to include this huge amount of dark energy. So that comes in almost 70% of some unknown dark energy component, but also one which resembles matter. So it's called dark matter. And so we have to introduce these two dark components in order to explain our observations within the standard paradigm and with general relativity as our theory of gravity. So that already motivates people to look for any deviations from this theory at large scales, at large cosmological scales. But there are other motivations to go beyond the standard model of cosmology. And so one other motivation would be from apparent tensions in data sets. So here we have a picture of the CMB, which is an early time measurement of the distribution of energy. And from that, we can infer some cosmological parameters. And then we can also make a similar observation at late times with the galaxy distribution. And we can see if the cosmological parameters from our early time and late time measurements match. And apparently, some tensions have been uncovered in these data sets. So the early time data sets and the late time data sets. Predominantly in the Hubble parameter, which gauges the expansion of the universe, but also in the amplitude of density fluctuations with lensing. So there's sufficient motivation to look for any deviation from lambda CDM. And that will be the motivation for all the things that I'm going to be talking about today. So that the beyond lambda CDM physics that I will be thinking of could be in terms of dark energy, so modification to the constant dark energy that the lambda CDM model assumes, but also modifications to gravity itself. Right. So let's move ahead and let's go to the information that we can extract from the galaxy distribution on the sky. So previously we saw this picture of galaxies on the sky, and one thing we can take from that image is how the shapes of these galaxies are distorted from gravitational lensing. So what happens is the background galaxies, the light from the background galaxies moves through the cosmic medium and through the dark matter distribution between us and those galaxies, and it gets lensed. So the light paths are distorted, and so we can construct from these distortions what are called shear maps. And within those maps, there's a lot of information about the dark matter distribution between us and the background galaxies. And this information is directly related to the cosmological model that we're testing. So how do we model this cosmic shear? So this the shear map. So this is the theoretical prediction that we have for that shear map. And what you can see from this is there are some standard cosmological parameters in there. There's the matter density fraction, and there's the expansion rate today. You have some redshift dependent kernels, but the key ingredient is this. So that is a measure, so it's the nonlinear matter power spectrum, which is a measure of how dark matter is distributed between us and the background galaxies. And that is intrinsically related with the cosmological model and gravity. So what I'll be talking about is how do we model this without assuming lambda CDM? So can we do that in a very accurate way without assuming the lambda CDM picture, the standard model? And a lot of work has been done on that front. In particular, I'll be talking about the reaction approach to model this quantity extremely accurately. And so the first paper in this series of papers came out 2 years ago. So it was this group in Edinburgh. And they came up with this idea of a reaction to a standard lambda CDM power spectrum, which could encapsulate modifications to the standard model. And in a second paper, a follow-up paper, they described how to improve the accuracy of this prescription to below % or at % accuracy down to K of 10. So when I say K of 10, that is extremely nonlinear scales. And it's essential that we model these scales when we are considering the lensing power spectrum or the cosmic shear power spectrum. Because since the light is integrated from the background galaxies to us, it picks up all this nonlinear structure information as it travels. And so if we don't accurately model the power spectrum or the distribution of dark matter between us and the background galaxies, then we will get a wrong picture of the cosmological model and gravity. And finally, in the third paper, which came up more recently, they described a way to include massive neutrinos in this reaction approach. So I've been talking a lot about reactions. So what exactly are reactions? So let's take a look. So it's a very simple formula. You have your nonlinear matter power spectrum as a function of scale and redshift. And that is, so the term on the left is a general nonlinear matter power spectrum. So you say, I want massive neutrinos, I want evolving dark energy, I want modifications to gravity, and I want you to give me the nonlinear power spectrum for that theory. Well, so that power spectrum is then equal to a quantity called the pseudo nonlinear power spectrum, which is an accurate nonlinear power spectrum which has lambda CDM physics. So that can be obtained fairly easily given what we have currently. And you want to include modifications coming from the new physics that you're introducing to this situation, this scenario. And so how do you model this reaction? And that becomes a key problem of this idea. So in the first paper of the series, they gave an ansatz for this reaction term, which was based on the halo model and perturbation theory. So the halo model is a nice framework which describes how dark matter halos, so clusters of dark matter, how they cluster between themselves and within themselves. And it's based, well, within this framework, you need 3 ingredients, basically. And you need 3 ingredients which describe the halos within the universe. So the first is the mass function. So it tells you how many halos of dark matter of mass m do we have in the universe. You also need to know how concentrated those halos are. So how concentrated the dark matter within those halos is. And you also need to know the density profile. So how does the density change as a function of radius within the dark matter halo? So these are 3 key ingredients for the halo model. And for lambda CDM, there are some very good ansatz for these 3 ingredients. So for example, the Navarro-Frank-White halo profile or the Scheff-Torman mass function are good ansatz for these quantities. The second part is perturbation theory. So I won't go into too much detail about perturbation theory, but basically you want to model your density contrast, so your density in the universe, perturbatively. So you treat it as a very small quantity. And so you say your density field is equal to some linear density field plus higher order corrections. So these higher order corrections go as powers of the initial linear density field. So one thing I should say at this point is that within these two frameworks, you can include, in principle, whatever physics you want. So they're extremely general theoretically. And so if you say you want a particular model, you can go within these theories and you can model it, and then you can get a prediction for your reaction. So in this way, we get a means of calculating the nonlinear power spectrum in a very, very general way, if you believe the ansatz that they provide. So let's take a bit of a closer look at this ansatz for the reaction. So in the original paper, this is what it looked like. So what we see is we have the one halo terms. So these are the halo model terms. So these are calculable within the halo model. But you also have one loop perturbation theory entering the modeling too. So you need to calculate the first order correction to your power spectrum coming from perturbation theory. And what we also notice is that the reaction without this term here is just a ratio of halo model predictions. And so the halo model is known not to predict the power spectrum very well. And in particular, it has trouble when you transition from the linear scale to the nonlinear scale. But it does model the modification coming from new physics fairly well. What they've done in the original papers, they've also included this correction term to the linear part of your modified halo model prediction. And so that term has been shown to improve the transition from linear to nonlinear regimes for modified gravity theories where you have screening mechanisms in place. And so I probably would just gloss over the technical details of this point. But this is well motivated in the context of modified gravity theories. Right. So now we're armed with a prescription for a nonlinear power spectrum for theoretically general theories, which can describe our universe. So let's move forward to see how these things, before I move forward to describe how these things fare against n-body simulation, I'll talk a bit about the parameterization. So how do we parameterize modifications to gravity in this framework? So the first thing is within the halo model, you can parameterize this in the Poisson equation, so the nonlinear Poisson equation, which relates the gravitational potential to the density field, the nonlinear density field. So you have this f function, which parameterizes your modification to this Poisson equation. But you also have to deal with the perturbative Poisson equation. So in perturbation theory, you have the same equation, but now it's perturbative. So this delta will be a perturbative delta. And so if you want to go to one loop order, which is required for the reaction, you need to consider up to third order in the density field. And so you have three kernels that you need to model, model. And so if you specify any theory of gravity or, well, I won't say dark energy for now, but if you specify a theory of gravity, these are all calculable quantities within that theory. So this is what I mean by theoretically general. If you want to modify dark energy, then you just need to change the background expansion, and there are some modifications to the virial theorem, but I won't go into that. So how do these things do against simulations? So when we simulate our universe and we solve everything exactly using numerics. So on the left-hand side, I have DGP comparisons to n-body simulation. And DGP is a 5-dimensional brane world model of gravity. So it represents a modification to gravity. And what we have here is we have the ratio of the modified power spectrum to the one in lambda CDM. And what we can see is that the reaction approach does extremely well, keeping within 2% accuracy down to about K of 2 and K of 3. For f of r, which is another modification to gravity, we get the same level of accuracy down to a similar scale, K3 or 4. For reference, if you were to model the power spectrum perturbatively, you would only realistically be able to go down to about K of 0.2. So this is over an order of magnitude improvement in the scales that you can accurately model the power spectrum at if you take perturbation theory as being your next general way of modeling the power spectrum. Another point to mention here is that the inaccuracies you see at even smaller scales, so when we go down to K of 10, this is coming from inaccuracies in our halo mass function, which we assume to be, which we take to be fitted to lambda CDM simulations. So we don't refit the halo mass function to the modified gravity theories. So improvements in the reaction itself, coming from improvements in these ingredients in the halo model, can also improve the accuracy of this prescription. And this has been shown in the original paper. You can also do this for evolving dark energy, where you obtain slightly worse at intermediate scales levels of accuracy. So this is a evolving dark energy model against simulations. Also, what we can do is we can go out and compare this approach to the current state-of-the-art modeling procedures for modified gravity models. So currently, one of the state-of-the-art, if not the state-of-the-art ways of modeling the f of r power spectrum is an emulator, which was proposed in this reference here. And here we compare the reaction approach in green with the emulator. So if you look at the bottom panels, the green triangles show that the emulator and the reaction approach are within 5% consistent down to K of 3. Right. One thing I forgot to mention is that another source of inaccuracy for this modeling is within the lambda CDM-like power spectrum you're using, which is multiplying the reaction. So here we use halo fit. Previously in this plot, we used HM codes, which are both fitting formulas within lambda CDM. And those are known to be about 5% accurate down to K of 3. So you would expect similar orders of inaccuracy when you compare to other more accurate methods. Great. So far I've contributed nothing to this. So that's all been background, and that's been the work that's already been done. And now I'll talk about what I've been working on for the past year, and in particular a paper that was released not a month ago. So it's a code. So we've written a code in C++ with a Python wrapper, which allows you to compute these quantities given some theory of gravity or dark energy. You can find the code over there, but if we have time at the end, I'll also go through a short tutorial on how you can use the code or download it yourselves. Great. So here's a very quick schematic. I know this is a bit of a boring slide and there's a lot to take in here, but maybe we can go through it slowly. It's a flow chart of how the code works. So at the top, you have all your standard model parameters, your Hubble, your expansion rate, power spectrum tilt, the matter density fractions, and the amplitude of your perturbations. And you also have now some additional parameters which characterize deviations from the standard model. So some new parameters, Phi. And these are fed into some linear power spectrum, which is then fed into spherical collapse, which is the halo model. You have these three ingredients, which I talked about before, the mass function, the concentration, and the density profile. And these all are used to calculate these quantities. So you have the unmodified lambda CDM-like halo model power spectrum and the modified halo power spectrum. As you can see here, we have our parameterization F, which is changing the Poisson equation, which is also going into this calculation. Also, this linear power spectrum then comes down this way and it feeds into the perturbative part of the code, which calculates the one loop components. You also need to feed in now your second and third order modifications to the Poisson equation. And then out comes the reaction. And that reaction, you multiply it with the nonlinear lambda CDM-like power spectrum, which you've calculated however you want. And out you get your nonlinear power spectrum. So what have we done with this code? The code is very fast, which is what we wanted. You want this basically, if you want to do any sort of analysis with data, typically you want a code which can compute things very fast. So you can compute many likelihoods in a reasonable time scale and plot out the probability distributions of your parameters. So this is a standard MCMC analysis, which we did with the code. And we considered f of r gravity to produce some forecasts for LSST, an LSST-like survey. So what we did is we took some lambda CDM lensing spectrum, so a cosmic shear spectrum, with a Gaussian covariance matrix with parameters which were typical of an LSST-like survey. And we compared to that data an f of r spectrum using the reactions and the code. So the modeling that we considered is React plus HM codes for the nonlinear lambda CDM-like power spectrum. And so what we find is that the parameter for f of r naught parameter can be constrained to within 10 to the minus 6, which is highly competitive when you think of ongoing and also finished surveys at the 3 sigma continents level. If we go down to multiples of 3000, so multiples of 3000 represent very, very non-linear scales, so very small physical scales. And that's why we want to model the power spectrum extremely accurately, so we can go down to those scales with confidence. If you don't go down to those scales and you only consider linear to quasi-linear scales, then your constraints on the parameters obviously significantly degrade. Keep in mind this is log 10, so minus 6 and minus 5.5 are significantly different from one another in terms of constraints. And one thing to note is that compared to a standard lambda CDM analysis, this takes 5 times longer because you have to solve one loop perturbation theory as well as spherical collapse. But it's still reasonable timescales to do such an analysis. All right, so that's the first thing I'll say. So now we have this code which can compute the nonlinear power spectrum and the lensing power spectrum for a given theory of dark energy or modified gravity. And what can we do with it? So one thing we thought of is, well, we want to go and model the clustering, the galaxy clustering power spectrum, which is not the same as the lensing, of course. And that includes various complications. So in this paper, we discussed some of our efforts to use this approach within clustering, within galaxy clustering. Here's a little Game of Thrones joke for those of you who follow Game of Thrones. So let me discuss what we did in this work. Maybe some background. So let's say I said we want to model the clustering power spectrum, right? So what is the complication when we think of the galaxy clustering power spectrum, or how galaxies cluster on the sky? So the main issue here is that we want to go to redshift space. So when we observe galaxies on the sky, they're obviously being attracted under some gravitational potential, and things collapse in a spherically symmetric way in real space. So if you have a gravitational potential at the center, all the galaxies will be moving towards that center, and the configuration will be spherically symmetric. So what you see here is what you would expect. But since we're introducing a line of sight direction, so we're looking at this thing, for example, from the bottom of the slide, the velocities of those galaxies are going to distort their positions on the sky, because the positions in the line of sight direction are given by the effective velocity of those galaxies. So in fact, if we're looking from the bottom of the slide, what we end up seeing is this. So the particular velocities of the galaxies are distorting their images, their positions in the z direction, or the line of sight direction. And so this effect, you need to take this into account in your modeling. It's a very large effect. And it's also very nonlinear, because when we think of galaxies or particles at the center of the cluster, they have very large velocities because the gravitational potential is so large. So the impact on their position on the sky is much larger. So we get these finger of God, phenomena. So how have people chosen to model this redshift space distortions, as it's called? So one model which has received a lot of attention over the past 10 years is the TNS model. And this was the flagship model of the recently completed Bose survey. And it's because it's been around for so long, people have extended it to modified gravity, and it's been tested against many different simulations. So it's a very well-tested, robust model. And it uses perturbation theory to model the redshift space distortions. More recently, this effective field theory of large-scale structure model has received a lot of attention. It's also perturbative, but they also treat nonlinearities using these counter terms. And it's also been used with data. So some recent papers have compared it to the Bose data. And these look very promising, offering slightly better constraints than the previous TNS model. It's been largely untested for any beyond lambda CDM physics, particularly modified gravity. So this is a current effort of the Euclid theory working group. And then you also have what are called streaming models, which take a slightly different approach to modeling the redshift space distortions. So you have perturbative and halo model-based approaches, and it has been tested for modified gravity with some public codes available. And so going back to this extension to React that we've done, within it, we've considered the streaming model approach. And the reason being is that in a way, we can include the nonlinear power spectrum in this modeling in a far more consistent way than would be with these other two perturbative-based modeling approaches. So why don't we want to be perturbative in this case? So maybe I'll outline some problems with perturbation theory. One issue is the loop expansion doesn't converge. Maybe I can gloss over these things because some of them are quite technical. For modified gravity theories, calculating perturbation theory power spectra can be quite slow. Like I said, the real to redshift space transformation is very nonlinear, so using perturbation theory is not sufficient. So in fact, the TNS and the effective field theory models both use some phenomenological or some free parameters, some degrees of freedom to model this nonlinearity. And also, if you're thinking of using both the lensing observable and the clustering observable at the same time, then you would really want the same nonlinear power spectrum going into both of them, just for consistency. There are various solutions to all these problems, but yeah, maybe I won't go into those. And like I said, the streaming model may offer a more consistent means of using the reactions for clustering. So what did we do? So what have we tried? We've basically just tried to Fourier transform what's known as the Gaussian streaming model. So I'll give you the expression for that. So this is called the correlation function. So it's basically a measure of your galaxy distribution in real space, and now it's not in Fourier space, in redshift space as well. And it's basically a convolution of your real space clustering. So here you have your real space correlation function with a probability distribution function of your velocities. And if we think of using React for this, well, the first quantity is easily modeled using React. We just Fourier transform our nonlinear power spectrum. The problem comes when we want to model this probability distribution function. So one, as the name suggests, one way is to assume this is a Gaussian, which has been shown to do fairly well. And then you only need to concentrate on modeling the mean of the Gaussian and the dispersion of the Gaussian. And there are very theoretically general ways of modeling those things. For example, perturbation theory, which is what we tried in this work. And so here I'm going to show you some comparisons of the different redshift space clustering models that I showed you in the previous slide for f of r. And so you have linear theory, you have TNS, you have effective field theory of large-scale structure, and you also have this hybrid model, which is the Fourier transform of this Gaussian streaming approach. And we can see that at the moment, it does competitively with the other models if we just consider dark matter. So it's promising, and we're going to dedicate some more efforts to developing this model in the future. So that's the end of the main section of my talk. I'll briefly go over some things we're working on currently to develop this framework further. So the obvious thing to do now is to include neutrinos and baryons, which are extremely important to model in the nonlinear regime. So if you're thinking of going down to very, very small physical scales, then baryonic physics become important. So you can't just think of the dark matter distribution. And also neutrinos play an important role, even on quasi-nonlinear scales. So including those in the code would be essential for even a standard lambda CDM analysis. And so then it could be very useful for standard analysis. Another thing, so this is why I spent some time discussing parameterizations. So as I said, you have these functions, the gamma functions and the F function, which parameterize the modification to the Poisson equations. And those need a particular theory to be specified before you can calculate them. So as I've done in most of the comparisons, I've chosen f of r or DGP as test examples. Ideally, what you would want is some general parameterization, some set of parameters which can characterize any deviation you could have from standard physics. And then you could compare this quantity in a likelihood analysis with the data and get constraints on deviations from general deviations from lambda CDM. So one example of such a general parameterization would be the effective field theory of dark energy. So we're dedicating some time to including general parameterizations within this code. When I talked about clustering, so this is another issue, when I talked about galaxy clustering, what I showed were comparisons for the dark matter distribution. And so obviously we observe galaxies on the sky, not dark matter. And so you need a model which relates the galaxies to the dark matter distribution. So this is the bias modeling. And so to have a model which you can compare to data, you need to model this bias. And that's something we are thinking of within the streaming model. And there are a lot of efforts currently going on to doing that, even within the HALO model. So Georgios Valogiannis has done a lot of work in this direction. And finally, for those of you who are interested, we're also working on reaction for the bispectrum, which is the power spectrum is the 2-point correlation, and the bispectrum is just the 3-point correlation of the galaxy or dark matter distribution. So if you could model the bispectrum as well, you could more wholly capture the underlying distribution of dark matter or galaxies. So it's important to have a prediction for that. Ooh, that's a spoiler. I should have. Anyway, let's move on. Hopefully I have some time to discuss a little side project I've been working on using React. And I just saw that the next slide is slightly ruined, but let's go through it anyway. So it involves machine learning. Right. So I'm going to show you 2 pictures. Ideally, that a Greek wouldn't be showing, and I would ask you which one is a Greek. And hopefully someone would say the one on the left is a Greek, because the one on the right is just Greek. And so currently a lot of machine learning efforts are being dedicated to identifying faces or people from images such as these. And they've gotten extremely accurate. So we thought, could we do the same thing, but with power spectra? So I hope, yeah, that's just Greek. Okay. Oh, I'm going to have to remove that. Okay, great. Let's go back. Okay, good. So I'm going to show you these two images. And so these are basically profiles, so like faces of power spectra. On the x-axis, you have redshift, and on the y-axis, you have scale in K, so it's log 10. And it's a contour plot, so it tells you how big the deviation from some reference spectrum is. One of these is a modified spectrum, and one of these is lambda CDM. And I would challenge any of you to guess which one is the modified spectrum. Does anyone have a guess? It's not as easy as Alkistis and a piece of theta. Yeah, okay, I'm gonna take that as no, because it's impossible. So what you can see is this one was actually a Favar, and this one was lambda CDM. So what we want to do is train an algorithm, a machine learning algorithm, in particular a neural network, to identify power spectra, to classify them as being lambda CDM or not lambda CDM, and perhaps even further, does this power spectrum have a Weinstein mechanism, or does it have a chameleon mechanism? Is there evolving dark energy in this power spectrum? So that's something we've been working on. And so using React, we've computed tens of thousands of power spectra or faces, and we fed it to this neural network, and we have some extremely promising results. So we get accuracy of classification, which is almost 99%. What I should say is using in the training data for this neural network, we've used DGP, F of R, evolving dark energy, and also random features. So we've added in random features to the power spectrum using some algorithm, which I don't have time to discuss. And we've also included lambda CDM spectra. So maybe just a word on where it misclassifies. So you say 99% is extremely accurate. So what does it get wrong? So the misclassified examples actually are, as you would expect, they have extremely tiny deviations from lambda CDM. So for example, F of R naught is 10 to the minus 8 in these two examples, which have been misclassified. So hopefully the idea behind this is, can we augment standard MCMC analyses? So if you have your standard MCMC analysis, maybe before that you could run this neural network on the data. You could say, okay, well, this looks like it has some scale dependency. Maybe we should test F of R with that. Or even before anything is done, you can say, okay, maybe this isn't lambda CDM, or this is completely consistent with lambda CDM. Some of us in the group are also talking of going beyond that and replacing MCMC altogether, but I'm not that bold. I'm not going to say that it will replace MCMC altogether. Great, so this is my last slide. So hopefully I've motivated some very interesting tools that are now on the market and methods that are now on the market to capturing the observables that upcoming surveys will be giving us. In particular, Euclid is right around the corner, and all this development is extremely timely in that context. But also you have many other surveys which are also upcoming, and hopefully we'll be ready for the data when it comes in with modeling that we can confidently apply it to. Thanks.
All right, thanks a lot. Yeah, do you want to show something with the code right now, or shall we leave this for after the discussion?
Perhaps it's better after the discussion. Yeah.
Okay, so then, yeah, so for the folks watching on YouTube, thanks for watching. I hope you enjoyed the talk. If you have questions, leave them in the comment section, and I'm going to stop the live stream now.